Hello everyone, I'm Nam. Currently, I'm the section manager for manufacturing decision support under the digital manufacturing division with ARTC. So in our section, we do two main application, predictive maintenance and predictive quality management. Yeah, today I will work with Dean to share with you some of our experience in predictive maintenance work.
Thanks, Nam. So I'm Dean. I'm the chief data scientist from DataRobot. So while Nam will cover some of the technical aspect of predictive maintenance, I will cover the strategic side of things, like how are we developing the solution and why this solution on the platform will be useful for you. So look forward to today's session. Feel free to put your question in the chat or later on Slido. So happy to discuss more. I will pass this over to Nam first and then to cover the technical side of predictive maintenance.
Okay, thanks, Dean. So I will share some technical challenge and some of the approach we can take for predictive maintenance solutions. Firstly, we talk about the maintenance approach in the industry. We basically have three maintenance approach. The very basic one is reactive maintenance, means then the other one is preventive maintenance and predictive maintenance, of course. So for reactive maintenance, basically repair are made only after the failure has occurred. Then for this maintenance approach, we will have low upfront cost and easy to implement. But we have a high risk on unplanned downtimes and cascading failures. So basically, we will say that reactive maintenance is just act like a firefighter. When the fire happens, then you try to collapse it. Then for the preventive maintenance, it's basically a scheduled maintenance based on times.
Sorry,
Yes.
are we sharing screen?
Oh. Okay. Okay, sorry about that. Yeah. So for reactive maintenance, it's basically we act like a firefighter, try to distinguish the fire after it happened. For preventive maintenance, it's basically a scheduled maintenance based on the times or usage of the equipment. So the purpose is to reduce the likelihood of major failure. Also may lead to unnecessary servicing or missed degradations. Basically, what we will do a regular checkup for the health of the equipment. However, this is a time-based approach, and we don't have any visibility of the health of the equipment in real times. Then the final elements is about the predictive maintenance. So we will use the machine data and AI to analyze and anticipate the failure. And it will enable condition-based and timely intervention before the actual failure happens. The major challenge is that it requires significant investment in data infrastructures and expertise to build the AI model. Yeah, so a typical dashboard of predictive maintenance is something similar like this, where you have the health score in real time, you have the remaining useful life in real times, and also you have the prediction of the proper failure root cause in real times. Then, and we all know that the major industry application, right? The main approach we are having now for maintenance activity are preventive maintenance. So some of the drawback of preventive maintenance are because it's a time-based and it's not a condition-based. So we will lack of the real-time health visibilities. We don't have any continuous monitoring of the asset status, and we will be into the risk of over or under maintenance. So if over maintenance, it will be unnecessary and increase the cost and avoidable downtime of the machine for maintenance activity. If it's under maintenance, we may miss some hidden degradation and leading to unexpected failure. And unexpected failure happen due to maintenance in the past. Some of well-known case like the Boeing 787 Dreamliner production issues in 2019 or 2020s. Yeah, the root cause of the issue was about the quality control and maintenance labs in tune calibrations. And then it will have the impact on the production delay, the aircraft routing, and then FAA security scrutiny. And locally in Singapore last year, we have major issues on the MRT line disruptions. The issue is again due to mechanical failure in the track switch. And this is the result of a time-based maintenance, and it may have missed the early warning sign. And the impact is, of course, luckily we don't have any injuries, but several track and system has been damaged, and the service has been suspensions on the affected line for nearly 2 weeks. So these are the real case. That's why preventive maintenance has its own limitations, and that's why we are here today to discuss about predictive maintenance. So the benefit of predictive maintenance, it can, based on our feedback from our collaborators after the project we did for the industry, it can help to improve the uptime 10 to 30%, have in faster troubleshooting 20 to 70%, lower the operational cost about 10 to 25%, and reduce the testing times. It's also have the companies to have a more systemized and integrated solution in terms of maintenance management, and also enhance the competencies of the workforce. Okay, so next I will talk about the element in the predictive maintenance systems. For predictive maintenance system, we start with the equipment in the production lines. We extract the data out from it, and we have additional sensor when needed to collect the parameters such as vibration, acoustic, power, operations, or visual informations. And we will convert it into a data pipeline. We store it into an offline data set. And we will need to have a domain expert to do the labeling of the data. After that, we'll train the AI model. We put it back to the server for online inference, and we have real-time predictions with operational dashboard for even condition, either condition monitoring, fault detection or diagnosis, or lifetime estimations. And with that, we have near real-time visibility for the operator in the shop floor to make the better decision for manufacturing. So a typical life cycle of predictive analytic projects. So as I mentioned earlier, the first step, we need to have a proper data pipeline, including the hardware connectivity, the middleware connectivity, and the data collection and preparations. This could take around a few months to up to a year or more, depending on the complexity of the equipment. The key technical issue we need to deal with is basically the customized sensor setup for a targeted data acquisition system. We need to coordinate with the operator in the shop floor to supply supplementary data. And we also need to have context-aware sampling to capture the full data distribution in the production scenario, especially for failure scenario. Yeah, if we want to do predictive for the failures, we need to have historical sample of the failure scenario in the past so that the AI model can learn and make the decision in real time. And also, we will need to convert multiple source data into an AI-ready format. So the data we are dealing with can be time series data, can be tabular data, can be event data, visual data, human input from the operator, and text data, basically the maintenance log. Yeah. Then the next step, after we have the proper data pipeline for the application, we move to the AI and ML model development. We will do the feature engineering to extract and labeling the useful features from the raw data. Then we build the model for the specific task, be it condition monitoring and abnormality detections, or assess remaining useful life predictions and fault diagnosis, or prescriptive insights and maintenance copilot support. Yeah, and then after we have the AI algorithms at the heart of the application, we'll need to encapsulate it with a software solution. So the software will need to be contextualized to the need of the customer. For example, different customer will want to see different thing on the dashboard, and the solution also need to integrate to the existing IT/OT system on the shop floor or enterprise level. And because of that, we will need some customization for different clients. And after that, of course, the maintenance and support of the solution. And you can see here, there are two different dashboards for two different applications. They can be very different from each other. Yeah. Then next, I will talk a little bit about the challenges in adopting predictive maintenance solutions. As we have three elements in the predictive maintenance solution, we will have three area of challenges. First, we talk about data challenges. Yeah, for a new deployment, usually we don't have sufficient sensor data. And because of that, we don't have a long-term trend. And without a long-term trend, it's very difficult for us to make an accurate long-term predictions. An illustration is here. For example, when we have the data samples in good condition only, then it's very difficult for us to make a very accurate prediction on when the machines may fail. And the second challenge is about the limited failure data. So in manufacturing, we have 90%, 99% of good condition samples, but we have just 1 or 2 cases of the failure scenario. And because of that, it form an imbalanced data set in terms of data science. And with that, right, there will be a challenge for an AI or ML model to learn and predict accurately. And the third one is the labeling issues. So for a different application, it will require a different domain expert to label the data. So this one, the data scientist won't be able to help you. Yeah, the industry clients, those operate the machines, those in the specific domain will be the best to advise which label for which kind of condition of the data. And with this, right, we will need to work very closely with the client teams, especially those operate the machine directly to label the data accurately. So these are the challenges in the data. And I will move to the second part, will be the model-related challenges. Basically, right, the model-related challenges is resulting from the data challenges. Because of the data challenges, the model selection will need to perform very carefully which model we want to use for which kind of task. Because ML may work well in a smaller data set, but it cannot give a very accurate prediction. Why? Deep learning will need a relatively large data set to perform well. And also, the AI model will be struggle with the rare failures or noisy data scenario. And because of that, we need to come out with applications such as the augmentation of the data, upper sampling for the minority subset of the data to deal with the imbalanced data scenario. Then the next challenge is that when the machine operates in the productions, you may have concept drift or domain drift, be it whether the sensor pattern shift over time or the pattern of the process shift totally when we move from one product to another product or one machine to another machines. With this, the AI model need to deal with different data pattern and to ensure the accurate performance of the model. And the third one is, of course, the generalization issues. We cannot have one model to fit on the setup. And for each of the deployment, we will need to either retrain or adapt the model to a new scenario. So these are the three challenge for the data and the model. And for the software deployment challenge, we will have some issue with or not the issue, it's a technical challenge for integration to existing system like CMMS or IoT platform or the legacy system in the shop floor. And also we have to make a decision whether we want a real-time prediction with lower accuracies, or we want a batch processing with a deeper analysis. So we need to make the decision in terms of balancing the speed and the cost of the decision making. And the third point will be on the model maintenance. We will need to have proper MLOps infrastructures to monitor the performance of the model over time and retrain and update the model when needed. Yeah. So these are the major challenges in applying predictive maintenance solution in the industry. Next, I will go into one of the case study to show you exactly how we deal with what a new deployment in terms of predictive maintenance. So this one is for the CNC machining process. The data here we will need to have from the controller. So in this case, we take a Makino CNC machine as the use case. It's a Fanuc CNC machines. That's why the communication protocol for the controller, we do it in the Forecast SDK to get the controller data. Additionally, we also need to install the sensor, be it a vibration sensor or acoustic emission sensor, to collect additional process data. And we also need another input from the operator to tell us the product ID, the material, the coolant information, and operating condition of the machines. And with this, right, we will have three sources of data. And the data pipeline will need to pre-process and merge the three sources of data into one single format where the AI model can understand, and also can start to do the analytics task. Then, yeah, this one is the case study dashboard for the CNC machining process. Here we will have two main tasks. The first one is to predict whether the current conditions of the spindle bearing of the cutters are still in good condition for operations. And then the next task is to predict whether the remaining useful lives of the spindles or the cutter is still sufficient. If it's not sufficient, then we need to recommend the activity for the operators. And then we also build in here Copilot for maintenance activities to guide the junior staff how to do the maintenance activity for the particular machines. So these are the major element of the predictive maintenance dashboard. Talking about the use case of the predictive maintenance management, of course, the use case I shared just now is for precision engineering, but in the past we have done multiple projects for auto storage system as well, for biopharma and medtech production lines, aerospace, FMCGs, electronic semicon, and also others. Maybe I walk you through some of the use case. For example, this case, medtech production lines. The problem statement is currently they don't have the visibility on the equipment conditions. And the requirement is no additional sensor is allowed to monitor the condition, because they need to follow a very tight certificate and SOP. And because of that, we can only use the triggering signal from existing SCADA data to make the predictions. And the key features of these products is we are able to identify the bottleneck of the production lines. We extract the SCADA data, analyze the trending of the timestamp, and apply oversampling to deal with the imbalanced data. And we can make the prediction of the normal condition with accuracy of above 85%. Yeah, with this, the company able to make a early decision at least 2 hours ahead for the production's activity. Then the second use case is for the side milling machines. So with this one, right, the company themselves doing the corrective and preventive maintenance strategies, and they face some issue for the unexpected breakdown. And There's a limited data-driven decision making for optimal maintenance scheduling, including determining the right time to replace the cutting tools or predicting when to service the main spindles. So in this project, we help the company to deploy the sensor, extract the data from the controller, develop the algorithms, and design the dashboard for real-time visibility. And with these projects, the company is able to reduce the manual activity in maintenance up to 30% and reduce the unexpected breakdown up to 20%, improve around 10% of productivities, and reduce the manpower needed for maintenance activity about 10%. Then the third use case is for pumps and motors. You can see that the dashboard here are very different from the previous case. The problem statement is on the maintenance risk, unsuspected failures, and disruption due to the preventive maintenance. And actually, the company exploring commercials condition monitoring solution, but the basic threshold approach from the commercial solutions doesn't have because a lot of false positivity due to the complex data pattern. And because of that, they cannot have a good decision support for optimal maintenance activity. And what we have done is we have them to enhance the data pipeline, because without a good data pipeline, you cannot build a good AI model for predictive maintenance applications. And then we also help them to build the predictive maintenance algorithms and the dashboard for 15 motors and pumps. And we are successfully deployed the fault detections and diagnosis algorithms to enhance the maintenance activity. So here, the feedback from the companies, we have about 30% of fault preventions from the solution, and reduce the maintenance activity about 20%, and improve the efficiency because the solution will tell you what are the potential root cause of the issues, and then because of that, it can help to improve the efficiencies of the maintenance activity 10%. Then the final use case I want to share is on the lift health monitoring. So this is to serve the maintenance activity at the HDB lift. In this project, we work on the sensorization to have additional sensor and measure additional information like the vibrations, like the loading of the lift, and then we also extract the data from the controller, and we aggregate the data pipeline and build the AI model. In this case, the AI model is an unsupervised learning to detect the abnormality and predict the overall condition of the lift and prioritize and manage the maintenance activities. And with this, we can help to prevent about 20% failure and reduce the maintenance activity needed about 20%, and improving the maintenance efficiency about 10%. Yeah, and the final application I want to share for today is the robotic assembly. Robotic assembly is a highly automated solutions. However, with the automatic solutions, the machine shells also need to tell you when it needs to be serviced, especially the critical component like the assembly tools. So in these projects, we have to monitor and predict the tool conditions and enable the smart features for the robotic assembly task by telling the managers whether the system or the station are still in good conditions. So in this particular application, the overall accuracies for the predictive maintenance task is over 99%. And with this, I would like to end my sharing. I pass to my colleagues, Dean, on the more deep discussion in the AI portion.
Thank you. Thank you, Nam. Happy to continue this. So What NAM shared is more on the technical side. How do we build the predictive maintenance model? What are the typical use cases and why it is difficult? So I want to take a different perspective to present this, because predictive maintenance is not just an AI application. It's not just about the model. It's also about the strategy that company use to construct this kind of AI capability. So I want to share some of the challenges that we have seen in this kind of implementing predictive maintenance, and how automation tools such as a DataRobot can help you to address this kind of thing. So why this is challenging? I think from NAM's presentation, you would say it is actually a very difficult problem. There are data challenges, there are model challenges, there's model maintenance challenges, and everything needs a lot of time to be developed on. The first challenge we witnessed is the speed and iterations to develop this kind of maintenance solution. This is my favorite quote from my client. He says he has more pilots than the British Airways. This is quoted from a frustrated business leader. He's not in the aerospace space industry, but he's doing manufacturing. So the pilots here he mentioned is certainly not about the pilots who drive the aircraft. It is actually about the POCs or POVs they run year by year. It means that a lot of projects, especially when they want to do something on predictive maintenance, it stopped at the conceptual level or at the POC level. They are not able to push it through implementation. The reason for this is because machine learning is actually a long process. From data to the application you want to develop, you will actually need to jump through a lot of hoops to make sure the model is developed with high accuracy, to make sure the insight is valid for actions, and eventually the model is monitored and managed properly. Any of this can actually go wrong. A statistic from McKinsey says that 85% of AI projects will fail. This is on average for the AI projects. For a challenging project such as predictive maintenance, the failure rate on the first try would even be higher. It means that any of this process, such as data processing, you may process the data and find the data is not good enough. Then you need to go back to the source data and collect new batch of data. When you build a model, it could be that the accuracy is not high enough. You need to keep on fine-tuning the model until you are happy with the accuracy. It could also be that when you are deploying the model, you find that the delay is too large and you can't make the decision in time. Or when you are monitoring it, you find out the situation on the shop floor is not stable enough for the model to consistently perform. So any of the failure over this process will cause the project to fail. Just to give you a sense how 85% look like, it is actually higher than the chance that Singapore rains. So given the past 2 weeks, I think everyone feels that it already rains quite frequently, but 85% is higher than that. It is also higher than passing the driving test on the first try. And it is higher than Kobe Bryant's free throw scoring rate. So it means that failing this kind of AI project on your first try is quite easy. What we need to do is to reduce the cost of failure and the investment to these failures. So that's why DataRobot provide you an automated solution to build this. So that on DataRobot, when you want to process the data, you don't need to prepare the data to all the details. You just need to drag and drop the data to DataRobot. We will check the quality and let you know if the data is good enough to create a machine learning model. And then DataRobot will help you to build dozens of models and test their accuracy and performance so that you have confidence in using them. All this is done automatically. So if you ask a data scientist to create, let's say, 10, 20 models, he may tell you to come back next week when he is confident about his 20 models. But DataRobot can do this within a couple of hours and give you different versions of the solution, compare them, and tell you which one have the best accuracy. So this is a key automation we do on DataRobot to save the time of building the model and thus save the investment to the potential failures. And finally, DataRobot is not only a model building platform, it is also a model operating platform. It means that once you build your model, you select a high-performing model, you can deploy your model on DataRobot. One of the challenge Nam was mentioning is that predictive maintenance is something requires continuous monitoring. So it is not just about building the model, it is also about making the model as your service so that the new data can come into the model and you can get continuous output. So this is exactly what DataRobot do in terms of ML ops, machine learning operations. We serve the model, we score the new data for you, and we monitor the performance for you. So with all these 3 steps automated, DataRobot is going to save your time in building a predictive maintenance solution or any machine learning solutions in general, such that even if the end result is not good enough, you will not invest or you will not waste a lot of time building this inaccurate solution. You can go back, change your hypothesis, and have another try. Usually, a predictive maintenance project will last for like 6 to 8 months. But with DataRobot, we can accelerate it to 2 to 3 months to explore and find the right solution for you. So this is to address the first challenge, speed and iterations. We use automation to help you to get a higher speed in development and iterate faster to deliver the value. Yeah. So this is an illustration of comparison of the traditional way and the DataRobot way. Traditionally, each iteration will take a long time to complete because you need to build everything and test it if it works. The cost of error is so high that people sometimes give up after the first failure. But in DataRobot, within the same amount of time, you can actually try 5 different approaches, 5 different hypotheses. 5 is just a hypothetical number. You can just try as many experiments and hypotheses you want. So you can fail early and fail fast. And various options can be used to solve this problem. Another example is in predictive maintenance. If you think about it, you can either predict it as a classification to see whether the machine will fail in next week or next month or so, or you can build it as a regression problem to monitor certain readings of the sensor to alert about the failure. Or you can, as Nam has presented, it could also be an abnormal detection type of algorithm. So all the different approaches need to be tested and tried to build a solution. That is why the automated model building can help you to achieve the goal faster and earlier. So this is the first gap we close. We try to close the value gap with automation. The second challenge we face or we observed in predictive maintenance is the ownership and the knowledge. What happens in most of the organization is that this is actually a true story from a semicon manufacturer. So when it comes to predictive maintenance or the manufacturing machine learning problems in general, it is usually the engineers who are on the shop floor who has the idea and has the data to do that. They are aware of the process, they are aware of the data collection, and they are aware of the potential failures they need to predict. However, normally they don't possess the skill to build the model themselves. So what happens is that they need to communicate to the data scientist team. Usually, relatively, it is a much smaller team in manufacturers to build this model. So they need to share the data understanding, they need to verify the use case definition, they need to validate the performance with a much smaller data science team. And then the data scientists need to build a model, and also they need to test the model performance with the engineers back and forth to deliver that. So apparently, in this case, there will be a lot of ideas generated by the engineers, and there will be a lot of requirements of the models to be built by the data scientist team. But unfortunately, data scientists in this case become the bottleneck of creating value because it is a small team. They need to work on the use cases one by one. So usually, what the challenge they usually face is that they have a long backlog of projects they need to deliver. They have a very tedious type of hypothesis they need to verify with engineers, and they need to act a lot from the engineer about their domain specifics or about the data. Because the bottleneck is here, the value that they can create is actually limited. So what DataRobot is trying to do is a try to democratize the skill of data science. So we start with the same team, the engineers and the data scientists. However, now we train the now we train the engineers to be able to use DataRobot to build a model and run some experiment. DataRobot is a low-code platform, so that even if the engineers doesn't know Python, doesn't know any programming language, they are able to build their AI or data science model by themselves. So they can actually run the initial experiments to test about their ideas. This is good for them because they know what is a challenge, they know the data, they know the process. So once they can operate something on DataRobot, they are able to establish the experiment and test the ideas. Only after the preliminary test is validated by the engineers, they can actually validate this further with the data science team. So you can see here, data scientists do not need to go through the whole process of understanding the data and define a use case. All this can be done by the engineers with the help of a machine learning platform. And for them, now they can focus on productionize those high-value use cases. Again, this can be automated in DataRobot. So the work that the data scientists need to do is actually more on the validation and the verification of the models that the engineers build and try to put them into production. In this way, they can actually operate more deployments in the unit time and thus create better business impact and create more value out of this. So the experiments the engineers will run is automated by DataRobot. And the productionalize, the deployment of the models can also be automated by DataRobot. So in this way, the whole process is streamlined so that people can actually build better and faster solution, leveraging the automation DataRobot provide to them. So this is the second gap we close. We close the expertise gap using democratization. Though, yeah, it is not only limited to engineers. It could be the traders, analysts, the planners, developers, whoever are familiar with data, who have the business hypothesis can actually run this by themselves. And this is how we actually enable them. So this is the actual course that we run in one of the semiconductor manufacturers to teach them what is machine learning and how they operate on machine learning. What you can say is that there are 2 phases and 3 tracks we have actually implemented for them. The primary phase is actually the 101 courses to teach everyone what is machine learning, what is DataRobot or ML, so that they can have an insight on what is this tool and how is machine learning going to help them. Of course, now we can also do this for generative AI. So we have generative AI 101 to enable people to understand what is generative AI, how to use generative AI in their works and life. So this is a primer phase. If people are comfortable with this, they can move on to the practical phase, where we have 3 different tracks to tackle different problems. The platform track is more on the platform admin and the data pipeline side of things. Usually it will be the IT team who take this track to manage the platform and also provide the data to this platform. And second will be the application track. So the engineers I mentioned just now would be on this track to actually operate on this platform, build models, get insight, and test whether this model will actually create value for them. Eventually, if they want, they become the trainer themselves. So some of the users in the first training become trainers in the last training. So this is how they can actually grow very fast. So all this takes less than 1 year for them to start from a practitioner to a trainer. And finally, there's also the management track. So there are some of the team leaders or even the CDOs, CEOs in the organization may not need to be hands-on to operate on the model, but they need to know how they should change their mindset in terms of delivering value using AI projects. So this is more of a roadmap and organizational change type of a workshop for them to learn about how to manage a team in the era of AI. So when we do all this, they are able to build the use cases much faster and identify the challenges much faster. So back to predictive maintenance, this is also important for them, not only on the working level to have the tool to solve predictive maintenance. This is also important for the engineering leaders to understand with the AI-driven predictive maintenance, how they should change the way to do maintenance. For example, traditionally, if it is planned maintenance, the team usually plan the capacity based on a schedule. But here with predictive maintenance, the workforce planning need to be more dynamic. They need to actually react to the predictive maintenance insights to prepare different assets, different manpowers for the maintenance actions. So when the more advanced solution is used to solve the problem, the way to think about the strategy about this process need to shift as well. So that's why this whole training is not only about how do you build a model, how do you tune the model, but it is also about how do you make the best of the model in your business or in your manufacturing process to create value. That's why this whole 3 tracks are actually very important for the companies to start use predictive maintenance or AI or any AI tools in that sense. So this is the second gap we close. We close the expertise gap using democratization and training. So for the next part, I want to show you a quick video on the tool we actually built for the predictive maintenance. So this is actually a good combination for Nam's part and my part. So you can see what is the predictive maintenance tool look like and why the platform behind it is efficient in doing so.
In military aviation, safety, reliability, and readiness are paramount. Ensuring aircraft are in peak condition is crucial for mission success. Let's look at how military organizations are transforming their maintenance operations with DataRobot. Our interactive dashboard provides real-time fleet status, including the total size of our fleet, our target capability, and our 60-day average historical capability, and preventative maintenance forecasting, enabling proactive decision-making and optimal resource allocation. At the command level, we can see overall fleet capability forecasts and individual aircraft readiness metrics. This comprehensive view helps commanders and maintenance chiefs optimize aircraft availability and plan missions and maintenance effectively. The system provides clear indicators of which assets most likely need attention and when. Powering these predictions is DataRobot's Enterprise AI Suite, which automates the end-to-end machine learning lifecycle. The platform evaluates hundreds of model types, selecting and optimizing the most accurate approaches for maintenance prediction. Both automated and custom Python models ensure we can capture complex maintenance patterns. The platform analyzes historical maintenance records, flight logs, aircraft specifications, and sensor data to predict when specific components will require maintenance and which operations should be prioritized for each sortie. DataRobot then evaluates dozens or hundreds of modeling approaches in parallel, delivering production-ready models in days instead of months or years, significantly outperforming traditional threshold-based approaches. Every prediction comes with detailed insights into the driving factors. The platform automatically identifies the most influential maintenance indicator in plain language and their relationship to the prediction. This transparency ensures maintenance teams understand and trust the model's recommendations. DataRobot's specialized time series capabilities automatically detect seasonality and trends, enabling predictions from hours to months ahead. This helps balance immediate maintenance needs with long-term planning. Once deployed, DataRobot's MLOps capabilities ensure predictions remain reliable. Continuous monitoring tracks model and data drift, while automated retraining keeps predictions accurate as maintenance patterns evolve. Robust governance features ensure models are managed with comprehensive controls and traceability throughout their lifecycle. Drilling deeper into the application, we can forecast individual aircraft status and component-level maintenance needs. The predictive engine identifies specific parts requiring attention before they fail, enabling proactive maintenance scheduling. In the event of a failure, in this case, our AHRS is experiencing some malfunctioning internal components, the AI assistant supports logistics and offers guidance on repair procedures, ensuring swift and efficient resolutions. The latest generation of our platform combines traditional machine learning with generative AI capabilities. This fusion enables natural language interaction with complex prediction data, automated generation of detailed maintenance reports, contextual interpretation of sensor patterns, dynamic response to maintenance queries, and real-time understanding of mechanic and part availability at each base. The integrated chat interface allows users to query predictions, access maintenance documentation, instruction manuals, inventory, understand the reasoning behind each recommendation, and even run forecasting simulations with DataRobot's what-if tools. In this simulation, mechanics can evaluate scenarios to test whether exposure to harsh environments increases the likelihood of fuel line blockages or leaks that require preventative replacement. This combination of precise prediction and intuitive explanation helps maintenance teams make informed decisions quickly, with AI assistance available 24/7. Additionally, the system can pull in mechanic availability by connecting to duty schedules, ensuring that the right talent is on hand to address any arising issues efficiently. Our applications are tailored to each use case and automatically adapt to each aircraft's unique data. That said, we recognize that every use case and application require a degree of customization. As a result, we built our applications to be flexible enough to adapt accordingly. Our teams work closely with your SMEs to customize each application to ensure we're providing as much value as possible. Moreover, once we customize an application for a specific tail number, our platform enables replication across all other aircraft types through reusable and composable templates. This ensures consistent and efficient maintenance solutions throughout your fleet, maximizing the value of your investment. Discover how DataRobot can revolutionize your maintenance processes. Visit our website to learn more.
Okay, so hope you enjoyed the video. It is actually an application we built on top of a B-52 aircraft maintenance. So just to recap what we have covered today, we talked about the predictive maintenance model. We talked about the predictive maintenance strategy. So something that we haven't addressed, but also relevant to this problem, is the data quality issue, the data linkage issue. How do you handle high frequency data, and how do you handle these IoT connectivities? So if you face this kind of challenge, please reach out to us. We have the experience of dealing all these issues as well. So we're happy to share our solutions in that space as well. So for the last 5 to 8 minutes, we can open up the Q&A. Feel free to ask us any questions through this Slido or through the, so just scan the QR code and ask your question on the Slido, and we are happy to address your questions. Oh, there are already 2 questions. What are the more common AI use cases within advanced manufacturing? Maybe let me share first, and Nam can share as well. So predictive maintenance is usually the biggest impact one, because the asset is expensive and the unplanned maintenance is actually quite costly. What we also see that is impactful is quality management in a lot of advanced industries. For example, in semiconductor, the wafer quality actually can be verified through image AI. So that is also a real use case we have worked with other customers before. An interesting use case is that in a lot of advanced manufacturers, they care about their worker resignment from the shop floor, because training a worker actually takes a long time. If someone very experienced is quitting, they actually lost a lot of productivity. So they actually use AI models to predict who will resign from the shop floor. And this actually gives them a lot of benefits and insights.
Yeah, maybe just to add on with Dean, for the quality, right? Dean just share about the inspection angle. I would like to share a little bit more on the predictive angle. So instead of verify the output quality using the inspection, using the computer vision technologies, we can also monitor the process parameters and make the prediction on the fly, whether the product outcome from the machine or the process will be a good or a defective product, and also the root cause of the quality issues. Other use case can be varied. For example, labor cost estimation, quotation estimations, even planning scheduling, we have some AI elements inside. Yeah.
Okay.
Yeah.
Okay, let's continue. There are lots of questions. We need to be quicker. How long does typical project will take?
Yeah, it's a very good question actually. For predictive maintenance, I would say that The major portion of the times will be on the data acquisition and preparations, because in order to make a good predictions, we need to have a good data pipeline and a good data set. With the AI portion, with the experienced and scientists and also some automation tools like data robot, we can do it in 1 month, 2 months. But for the data preparation, it can take several months to get enough failure scenario. Yeah.
Yeah, so while I talk through this question, I see someone requesting the QR code. So with Data Robot, we are able to accelerate some of the modeling process, but I agree with them, particularly to predict maintenance. The data you need to collect enough data for the pipeline. One particular example is that most of the case will need you to show your failure to a certain degree. If we don't know anything about the failure, if your machine have never failed, it is difficult to start a predictive maintenance from scratch.
Yeah.
So at least we need to have a sense on the failures that happens on different part of the machine to get started. I think this also relate to the next question. What are the information we need to embark on the journey? So if the journey means predictive maintenance journey, I think Nam and I just talk it through. So we need to have some of the data, either the sensory data or the parameter data or the failure data from your process to do. If the journey refers to the whole AI journey, I think it is we need some problem statement from you,
Yeah.
like what exactly you want to solve for. Sometimes I phrase this question as like, if you have a crystal ball,
Yeah.
what do you want the crystal ball to tell you? So
Yeah.
maybe that's a starting point. We can build some AI tools for you.
Yeah, maybe I add in a little bit, specifically for predictive maintenance projects, right? At the beginning stage, we usually have a checklist to discuss with the companies to know whether your data pipeline is ready to a certain level, to know whether your operators are aware of AI technologies, and are they ready to do the labeling task for the data. And with those kind of feedback, we can know whether it is reasonable to start a predictive maintenance solution now or just to start the sensorization and connectivity solution. Yeah.
So AI hallucination, I think this is more for the generative AI part.
Yeah.
And Gen AI may hallucinate. So Data Robot actually have solution on that. It will take another workshop to walk you through in detail. But what we do is that we leverage predictive model to ensure the generative model is producing relevant and factual result. So a general way to do it is that we will compare whatever generated by generative AI with some grounding truths. For example, the maintenance manual or the machine's equipment introduction. So we can actually verify whatever information provided is not hallucinating, it's actually verifiable. So yeah, so this is what we talked about, the model monitoring. And guardrail part, it is certainly very important for AI, and we do have the tool to do that.
Yeah, basically the ML ops, right?
Yeah.
So I will take the next question. How we can ensure that our data is secure? Yeah, this is a very critical question actually. To ARTC, right? The common way we do this is we bring the toolbox to your company and we deploy the solution on premise or on the cloud service that you are trusted. And then for Data Robot, I believe.
So we also support on-prem installation.
Yes.
For some of our like more secure the client, we do need to install our platform on the infrastructure. But what we observe is that with the rise of generative AI, there are more and more clients open to cloud solutions because they understand if they want to use Gen AI, the most powerful Gen AI would be a cloud solution instead of like on-prem solution. So this gives them the opportunity to explore some of the cloud solutions as well. So generally, to ensure the data is secure, either we install everything on your premise so that it will be as secure as any of your IT system is, or if you trust any of the cloud providers, we will go with a cloud provider to provide to you. So usually this kind of security is not provided by the predictive maintenance solution alone. It is provided by the whole AI stack that you want to use. Yeah.
How much data on how far back do we need to prepare? Like
The,
Dean
the more
shared,
the more the better.
like Dean shared earlier, we should have some failure samples.
Mm,
So in our way, we usually ask the clients to provide the data point from at least the last maintenance record.
mm.
So at least we have one full cycle of data, then we can build a meaningful model. Yeah.
Mm. Yeah, so I will take the second part of it, like what is the best practice
Yeah.
to support the team take the first ever step. I would say we target some low-hanging fruit. So instead of like doing predictive maintenance, as we have discussed, it maybe take you 4 to 6 months to do the entire project. So instead of like doing this in one go, maybe you aim for something that is smaller but useful for the team. For example, we usually treat as maybe the maintenance is difficult to predict, but the production time is something more predictable. So if you can show to your team, there's an AI solution can make some accurate prediction according to your manufacturing process. That may be the first step. Then we can steer from there saying that, okay, predicting the time is not impactful as predicting failure. So we look into failure data and to predict maintenance. So we always try to aim for some low-hanging fruit, but yet valuable use cases first. It is not necessarily to be the predictive maintenance as a holy grail, but we can start with something smaller. How does DataRobot enables and facilitate the monitoring for deployed model part?
Yeah.
So if you deploy a model in DataRobot, it will be automatically monitored. It is actually more difficult to turn it off than turn it on. So what we realize is that as soon as people start to serve the model needs to be monitored. So it is actually automatically turned on. And what we do is that we will do 3 things. First thing is that we will serve the model. So the model will, when you deploy the model will come with the API calls enabled. If you have new data to be scored, if you have new insight to be generated, you can actually call the model through the APIs. So this is the serving part. The second part is that we will compare the model performance with the actual data that comes in. For example, if we are predicting maintenance and the machine actually fail, we inject this kind of failure information to the model and compare to our prediction to see if we need to adjust the model or if the prediction is accurate. And finally, we will retrain the model, meaning that if we do see the model is no longer on track, if we do miss 1 or 2 of the maintenance, what we will do is that we will try to leverage the latest data or the smaller scope of the data, particularly to the machine, to retrain the model so that the model can be more accurate. So I think under the hood of monitoring, the serving, monitoring, and the serving, tracking, and the retraining are the 3 things we do. Happy to elaborate more, and please reach out to us if you want to find out more.
Yeah.
Yeah.
Okay, thank you, Dean and Nam. Actually, I realized that this is 3 minutes past 12.
Okay.
So I think if we can still take in more questions probably offline later on. We can actually so for those that wanted to know more, this webinar is going to be available as an on-demand as well. And so in that we will also share the information on where you can share more questions or ask more things. Okay. And I think with that we can close this meeting. And in this webinar, I would like to say thank you again to Dean and Nam for doing this today. And thank you everybody for joining us today. Thank you.
Thank you.
Yeah, thank you.